Okay, so we are looking at knowledge representation and we were looking at properties in particular, uh, and we introduced this notion of reification. So, as I said, basically the idea of reification is to introduce abstract objects, and by this we mean objects which are not in the domain, but which are introduced by us into the domain, kind of injected into the domain to help us reason about certain things. So, in particular we were looking at properties, and properties like height, weight, distance, let us say volume, temperature. These are properties that we often associate with certain objects in the domain, and how do we represent these properties essentially. So, what we had said was that all these kind of properties are types, which means for example, that if we have a type of height, contains elements that correspond to height. And these elements are abstract elements in the sense that they are not concrete tangible things that we can see. So, if you say something like height Mary, then we say height Mary is an object of type height. Okay, so, I am overusing the overloading the term height here. In the first instance, height is a function which when applied to Mary gives us a new term. In the second instance, it is a type, which means it is a unary predicate which defines a certain type of objects essentially. But so, there is a little bit of overuse here, but we can think of all these properties like height, weight, distance, temperature as types, and any element of this type is basically a property of this type essentially. Now, so we can think of it as in the domain D, we add a new set called height, and then if we have Mary as an object in the domain, then the function height maps Mary onto some element inside this, which is the height of Mary. So, we can think of the height as a abstract object. Now, unfortunately, that does not help us enough to talk about height, because when we talk about things like height, weight and distance, we want to use units of measurement essentially. So, we may want to measure height in feet or centimeters or meters. So, the height of Mount Everest is so much and so forth. So, we want to come up with tangible quantities essentially. So, what we can do is, when we talk about units, we can think of them as functions. So, for example, units like inches and feet and so on essentially. And one way to think of these functions is that these are functions. So, for example, feet we can say is a function from numbers to objects of type height. So, when you say 6 feet for example, then essentially you are saying it corresponds to some element belongs to height. And then we saw that we can, if you want to talk about the statement Mary is 6 feet tall, we can represent this as height Mary, which we have seen is a function which maps onto an object of type height is equal to feet 6. So, we have also seen that feet is a function which maps numbers to height. So, so it takes 6 as a argument and tells us that what is the height of Mary essentially. So, we can talk about comparison now. Supposing we have the sentence Mary is taller than Peter. So, one way we can do is that define an ordering on elements of type height. So, once we define an ordering, then we can define what do you mean by taller and things like that essentially. So, we can make a generic statement. We can say that if you want to say Mary is taller than this thing, we want to say that there exists a number n and there exists a number m such that height Mary is equal to feet n and remember this is a statement in FOL equality, when we can equate two terms and say that they are equal, and height Peter is equal to feet m and n is greater than m. Notice that we have expressed the statement that Mary is taller than Peter without really talking about their actual heights. Essentially, we are saying that there exists some number n which is the height of Mary, and there is another number m which is the height of Peter, and n is greater than m essentially. So, we can express statements like this in FOL as well essentially. Now, we have this problem of supposing we say that let us say John walked for 3 kilometers and then ran for 900 meters. And the question is how long, how much did he travel? You know, these kind of problems occur all the time in kids books when they are learning maths, and we should be able to devise mechanisms in which we can represent such problems and solve them essentially. So, one of the questions that we have to answer is how does one add 3 kilometers to 900 meters. That means, we have to somehow find the conversion from one type to another type. Notice that this 3 kilometers and 900 meters, we will assume they are of the same type height, or I should have called it as type length, it does not matter, but basically it is a one dimensional measure and it represents objects of one dimensions essentially. So, how do we add 3 kilometers to 900 meters? So, obviously, when we talk about addition in this domain, then we have to talk about saying that you must always convert them into the same units and only then you can add essentially. How can we convert 3 kilometers into 900 meters? We can say that anything in kilometers is equal to something in meters x. So, let us say this dot represents multiplication into 1000. So, once we have represented somewhere that he walked for 3 kilometers, then we can make an inference using this statement which says that. So, this is basically for all x, anything in, if x is in kilometers, then if you multiply x by 100, then that is in meters. So, it gives us a mechanism for this thing, and then we can have rules which say that you can add only numbers in the same units essentially. So, I will leave this as a small exercise for you to figure out how to do this essentially. We can say that feet, instead of it being a function from numbers to objects of type height, we can say it is the other way round, height to numbers. And then if we want to still say that Mary is 6 feet tall, then we can say that so the same as before, that we have Mary, then we apply this function height to Mary. So, we get an object of type height, but now we have a function called feet which we apply to this object of type height, and what this gives us is a number, and that number is 6 essentially. So, this is an alternate way of looking at it essentially. Now, we can define an ordering amongst feet, just as we define that Mary is taller than feet, we can define an ordering of the number returned by feet. We can say that feet x is greater than feet y if x is greater than y. Now, if I want to talk about statements like the following, that Mary was, let us say, 4 feet tall in 2006. So, maybe Mary is a young girl, or she was a young girl in 2006 and she was 4 feet tall. How do I represent this kind of statements? Any ideas? Which of the two alternatives that we discussed about representing height is a better suited this thing? Because now I want to do something like the following. I want to say that so remember we are talking about ad hoc predicate choices. So, I will choose a predicate called height, which is still more overloading the function, the name height, and then I would say for this, when I talk about predicate height, I will talk about a person or a thing and its height and maybe a date followed by that essentially. So, my schema becomes as follows, that height, subject, height, date essentially. Now, which one do you prefer essentially? Do you prefer to talk in terms of abstract objects, or do you prefer to talk in terms of numbers essentially? The second schema that we are seeing right now essentially brings everything down to numbers, which of course makes things like addition simpler essentially, because if you say that he walked for 3 meters and he walked for 6 meters, then essentially both are 3 and 6 are numbers and you can add them up, provided of course we are talking about the same units. So, maybe in this mechanism it kind of makes sense to say that okay, since I am saying Mary is 4 feet tall, this kind of naturally corresponds to this representation. So, I could use this representation and use that as the term essentially. We are so used to thinking in terms of numbers that we have not thought about representing numbers at all essentially. How can we represent numbers? I told you a story last time about McCulloch, and he told somebody that I want to spend my life studying what is a number that a man may know it and what is a man who may know a number, and he was told that it is a job of a lifetime. So, when I say if I say Mary has 6 apples, what am I really saying? If you want to boil it down to some really concrete representation, whenever I use a number, what am I trying to say? What is a number essentially? What is 6 essentially? When I say Mary has 6 apples, what am I really saying, or what is this a shortcut for essentially? If I want to explain to somebody, let us say somebody comes from Mars or somewhere and you say that I will give you 3 apples, and the creature says, what do you mean you will give me 3 apples? Then you have to explain, what do you mean by 3 apples? Yeah, but if I want to define numbers, let us say I want to define natural numbers, I want them to be these discrete objects in my domain. These are reified elements I am adding to my domain. I may have apples and oranges in my domain, but now I want to add numbers also, in the sense that I want to be able to count and add and subtract and do all this kind of stuff. But what is this number? How do I add numbers to my domain in a logical sense?
Numbers actually define a sequence.
They define a sequence, all right.
So, when I say 1 and 2, I mean that one quantity is higher than the other.
Yeah, but that is after you have defined them, right? I think. How do you define them? It is a interesting question essentially. So, without spending too much time on this, and anyway this is not our main goal here. We can see that numbers correspond to set. So, the first thing that we are talking about is that somehow numbers are associated with sizes of sets. So, a number is a cardinality of some set. So, we define, as you said, a sequence, but we define a sequence of sets, and essentially we talk about cardinalities of sets. And when we say that Mary has 6 apples, we are saying that the set of apples that Mary possesses is in 1-to-1 correspondence with a set which I will call 6. So, this 6 is the name of a set, and essentially when I say that Mary has 6 apples, what I am fundamentally saying is that the set of apples that Mary has is in 1-to-1 correspondence with a set which I will call 6 essentially. And essentially, so this notion of quantity becomes a notion of a definition in set theoretic terms again, and we are saying that numbers essentially correspond to sets of certain sizes essentially. So, it is also an abstract notion that so some people have said that 6 corresponds to the set of all those sets which have cardinality 6. Now, of course, this is a little bit of recursive definition, but in some sense they all have the same cardinality. So, the set of 6 apples and set of 6 oranges, what they have in common is that the cardinality of the two sets is 6 essentially, and 6 essentially corresponds to this abstract concept of cardinality of a set essentially. Now, it was due to Johann von Neumann that we have a very nice definition of numbers. So, this definition works like this essentially, that the number 0 I give a name to the empty set phi essentially, which you can write it as an empty set phi. So, 0 corresponds to the empty set essentially. So, if you have nothing, then you have as many objects as an empty set has essentially. So, that makes kind of sense. The number 1 corresponds to a set which contains 0 and the contents of 0, which is the empty set. So, the number 1 is a set which I make by taking the set 0 and adding it to a set, and to that set I add all the contents of 0. So, you must remember that numbers now are sets essentially. So, how do I get that number? So, I got 1 by saying it is a union of the set containing 0 union 0. If I look at the number 2, then I am saying that take the set containing 2 and take the union with the set 2 essentially. If this makes any sense, it will make sense provided you remember that the numbers are union themselves essentially. Sorry, not 2, it should be 1, the previous set. And what is the set 1? 1 is this set that we have just drawn here, which is phi phi. This is the number 1. So, I put this, I want to take a union of this with the same set. So, the first object is a set containing 1 and the second object is 1 itself essentially. So, 1, the set containing 1 union with 1 essentially, which of course gives me the set of these 3 objects, the set containing the set containing phi and phi. Sorry, I am taking the union, so I won't have this. Okay, I think I messed it up. So, let me just start all this all over again. So, a nice idea of what numbers are was given to us by John von Neumann, and what he essentially says is that you start off with defining 0 as an empty set, which we can write like this. Then we define the number 1 as the set containing 0 union with 0. So, if you substitute what 0 is, which is phi, which is a set containing phi union with phi, which is a set phi itself, because if you take the union of anything with an empty set, you get that number essentially phi. Now, if you define the number 2 as a set containing 1 union with 1, the set containing 1 is this set which contains 1, and we are taking a union with 1, which is this set itself. So, notice that when I say 1 here, I have got 1 here, and when I say this 1 here, I have got this 1 here, which is equal to the set which contains phi and the empty set. So, the basic idea is that a successor of a natural number n is defined as the set containing the number n union with the set n essentially. So, we can now talk about the number 3. So, it is a set containing 2 union with 2 and this is we just wrote the set containing 2. So, if we take the set containing 2, so I just do a shortcut here will be this whole thing then the elements of that set which is the set containing 5 and then let us see. So, you can see here that the number 3 corresponds to a set which has 3 elements essentially. So, in this way we can define the set of natural numbers starting with the empty set by saying that the successor function defines a set by taking the previous number and taking a union of the previous number with a set containing the previous number. So, essentially. But when we talk about natural numbers for the rest of this course, we will essentially talk of this sequence. We will say that 0 which is a constant that we often think of, then successor of 0, then the successor of 0, and the successor of 0 and so on. So, in the end we will end up defining a sequence of elements in which the successor function is implicitly defined, and we have a definition that if you say what is the number 2000, you can say it is 1199 union with the elements of 1199, and so in some sense we have a logical definition for every set essentially. So, we can construct a set of that many elements, and that definition of that set of that particular cardinality is a definition of the number itself essentially. So, in the next class we will come back to reification and we will try to see where are the other places that we need to do reification.